Let's take a look at an example of a goodness of fit problem where the expected distribution is uniform. So for this problem, births by the day of the week, a doctor claims that the number of births by day of the week is uniformly distributed. To test this claim, you randomly select 700 births from a recent year and record the day of the week on which each takes place. The table shows the results. At alpha equal 0.1, test the doctor's claim. Okay, so I went ahead and wrote the hypotheses. The null hypothesis for goodness of fit is that the distribution is as expected, and for this particular problem, the expected distribution is uniform, versus an alternative of the distribution of number of births is not uniform. Okay, so it's as expected or it's not as expected. Okay, what I did was I previously put the observed frequencies in list 1. Okay, so if we look back at the problem, out of the 700 births, 65 were observed to happen on Sunday, 107 happened on Monday, and so on. So I went ahead and put those into the calculator in list 1. Now to calculate the test statistic, I'm going to need the expected values. Okay, so remember the test statistic formula for a goodness of fit test is the sum of the observed values minus the expected squared over the expected. Okay, so this is really easy to deal with when we have an expected distribution that's uniform. Since we have 700 births and we're assuming from the null that they're all equally likely, the expected value for each category or each day of the week would be just 700. Okay, so in other words, the expected value for each category would be 700 times 1/7. Okay, I get the 1/7 from the fact that there's 7 days in the week. Okay, so for each category we're expecting 100 births. Okay, so let me generate a little table here of the observed and the expected. Okay, so for Monday, the observed was 65, Tuesday was 107, Wednesday was 117, Thursday was 115, Friday was 114, Saturday was 109, and Sunday was 73. Now, for the expected values, since we're expecting a uniform distribution, the values would all be 100. Okay, so now we have our pieces to put into the test statistic by hand. So if you wanted to do that by hand, you would have to write out 65 minus 100 squared over 100. Okay, the first category, and then add it to 107 minus 100 squared over 100 for the second category, and so on. Okay, all the way down to the last category, which would be 73 minus 100 squared over 100. Now, this might be a bit cumbersome to do by hand. You could factor out 1 over 100 because each of these terms has a denominator of 100. Or we could just go ahead and do the goodness of fit test in the calculator. Okay, so I need to put in my expected values in list 2. I know those are all going to be 100. Okay, so I have a list of 7 values, all 100. And I'm going to press on Stat, right arrow over to Test, and then scroll down to the chi-square goodness of fit. Okay, the GOF stands for goodness of fit. Okay, so it's going to ask for my observed values and my expected values. My observed values were in list 1. and I put my expected values in list 2, so I need to change that. The degrees of freedom for the goodness of fit test is the number of categories minus 1. Okay, so I have 7 days of the week, or 7 categories minus 1, that would be 6. And then calculate. Okay, so if I had done this entire summation by hand, I would have gotten 27.94. Okay, and the corresponding p-value is extremely small. Okay, so the p-value for this test statistic is about 9.64. Oops. 9.64 times 10 to the negative 5th power. Okay, so if you wanted to, you could have put in 4 leading zeros than the 964. Okay, so our level of significance for this problem is 0.1. Okay, so comparing the p-value of 0.000964 approximately to our level of significance of 0.1, the decision will be to reject the null. And in fact, we would be rejecting the null at all common levels of significance since this p-value is extremely small. Okay, let's go ahead and find the critical value. And like I said in my previous example, the chi-squared goodness of fit test is always a right-tailed test. So I want 0.1 amount of area in this upper tail, and my degrees of freedom, number of categories minus 1, and that'd be 6. Okay, so taking a peek at the chi-square table, for 6 degrees of freedom, 0.1 area in that right tail, I get a critical value of 10.645. Now our test statistic of 27.94 is way out in the tail. Okay, so we're rejecting the null strongly. Okay, so the decision is to reject the null, and the conclusion would be that there is insufficient evidence to support the claim that the distribution, sorry, this is easier to type, distribution of the number of births is uniform. Okay, so we're saying there's not enough evidence to support the claim that we have a uniform distribution. Okay, and again, I did this in my previous example. If you don't have a built-in chi-square goodness of fit test, you can still get the test statistic of 27.94 indirectly. Okay, so let me go over that. Okay, so I'm going to go back to my calculator, go back to Stat, and go to Edit. And in List 3, I want to highlight, so arrow up so List 3 is highlighted, and press Enter to move my cursor down. I'm going to literally put in here an expression for the test statistic. Okay, so it's going to be opening up parentheses, List 1 minus List 2, close parentheses. Okay, so this is the observed minus the expected, squaring that, and then divide by the expected. Okay, or I could have put in List 2 here. Okay, so that might be a little bit more clear. Okay, so if we didn't have a uniform distribution, you would put divided by L2. Okay, so I'll press Enter, and then it will do the calculation for each piece of that test statistic. In other words, this first entry of 12.25 would be this first value here. the 65 minus 100 squared over 100. Okay, so I want the sum of all of these numbers, so I don't have to write them all down on a piece of paper and add them up. I can have the calculator sum that for me. So I'm going to go back to Stat, right arrow over to Calc, and then I want one variable statistics on that third list, and then calculate. Okay, so you'll see that the summation here, the sum of all the values, is 27.94. Now, unfortunately, this won't give you the p-value. You need the built-in goodness of fit test. However, you could go ahead and get your test statistic here and compare that to the critical value.